Okay, are we ready?
Ready.
Okay, so yeah, now we're at the really dicey part of the night. But I'm happy to be back talking about, this is, I guess, officially the discrete set theory portion. We're not going to be doing a comprehensive view of discrete set theory, but we're going to be talking about some very cool results. So let's get into it by just saying very briefly, what is set theory? What do I say when it's discrete flavored? There's much, much more than the results we're going to talk about today that fall under this umbrella of discrete set theory. So when we're talking about set theory, we're going to be thinking about starting with a base set of a finite number of elements. So for concreteness, you can say the integers 1 through n. And thinking about families of subsets here. So you have a set where every element in your set is a set that is some subset of 1, 2 through n. And much of set theory on the discrete side says, okay, if you have a family of subsets of some set here, what can we kind of infer about its properties and structure if you have just some partial information about it, such as, the size of the family, some information about how certain elements in the family intersect, things like that. So this is a, very vague couple minute spiel I'm giving, but the single set theory theorem that we prove today is by far not the only such theorem that you can prove. There's actually a really big and still research active field that deals with a lot of questions of this flavor. That said, so we're getting this set theory representation through the medium of really just one discrete set theory theorem. And to motivate this, let's look at an introductory example. So we've got a problem here similar to a real life situation that I'm about to move into. I'm currently at Iowa State University, but I'm moving to Truman State University in Kirksville, Missouri next year, which I'm very excited about. But it's a very small department, different from the very large department where I currently find myself. And so let's imagine a very small math department where we've got 5 classes we absolutely have to cover: algebra, business calc, ordinary calculus, discrete math, and an elementary ed class.
I don't see extremal graph theory in that list of classes. Must cover.
This is sure. It's really sad. I racked my brain for 5 minutes. I was like, what class starts with an E? To be fair, I feel like extremal graph theory, it's called topics in combinatorics, Corey. But so we've got these 5 classes that need to be covered. We've got 5 professors who are going to cover them, and each professor is going to cover exactly 1 class. We also have every professor submit to the chair a list of the classes that they actually want to teach. So first professor would be okay teaching algebra or discrete math. Second professor would be okay teaching business calc or standard calculus. Third professor says they'll do business calc, standard calculus, or elementary ed. The fourth professor is picky. They will only teach elementary ed, happily. And the last professor would be happy with either calculus or discrete math. Okay, so I asked, does there exist a harmonious assignment of classes in this department? I haven't defined what harmonious means, but putting that in scale, you can imagine you would not like to, if you're the chair, meet somebody who you gave a class that they hate, and every single day when you meet them in the hall, they're like, I'm teaching business calc, it really sucks, thanks, Carl. So you'd like to make an assignment where everybody actually teaches a class that's in their set of classes they want to teach. So let's just look at it for a second and reason through, okay, can we actually assign these classes to these 5 professors in a way where everyone's going to be happy? Professor 4 definitely would have to teach their one preference. So once I say, okay, I'm going to assign a class to one professor, I'm going to cross it out if it's on anybody else's list. Fortunately, not that many people wanted to teach that class, so we don't have to cross that much stuff out. And then let's see. Now I see that having crossed out that class E, professors 2 and 3 now have the same sort of available classes in their preference sets. And there's 2 professors with each of them have exactly the same list that has 2 things in it. So if both of these professors are going to be happy, then one of them has to teach calculus and one of them has to teach business calculus. It doesn't actually matter who teaches what. So let's say this guy teaches business calc. This person teaches not business calc, normal calc. And then happily, what's left over, algebra and discrete math. Well, I do have one person here who wants to teach algebra and one person here who wants to teach discrete math. Okay, so that's not a QED, that's just looking at some things and making some circles. But this is the type of motivation for the problem we're about to talk about. Okay, so what did we actually find here? We found what we would call a system of distinct representatives for the family of sets that I drew up here. So formally, what is a system of distinct representatives? It's if you have k sets, it's a list of k elements such that all these k elements in your list are distinct, and the ith element is in the ith set. So it looks just like this. You go through and you circle one element per set, and you do so in a way that you never circle the same element in 2 sets. And as you can see, systems of distinct representatives have like applications in terms of this is how you could think about making some assignment that people are happy about or something like that. So Hall's theorem, in the phrasing that we're going to talk about it today, talks about what conditions on a family of subsets I would need to guarantee that I can find a system of distinct representatives. And actually it tells me not just, okay, if you satisfy this condition, then you can find one, but it gives me an if and only if characterization of families of subsets where a system of distinct representatives exists. By the way, if you've seen this before, a couple of comments. Firstly, you might be thinking Hall's theorem doesn't look like this. Hall's theorem is a theorem in graph theory. We will talk about sort of rephrasings and things that are equivalent to this. So there is a way that you can parlay this into a fact about graph theory, which you might be more familiar with. You might have also, on a cultural note, heard this called Hall's marriage theorem, because originally the motivation for this was not making class assignments. It was like if there's men and women in a village and people have lists of people they're willing to marry, can we like pair them all up in a way that no spouses will hate each other? I don't know. I feel like these days scheduling classes is a little bit nicer, but if you hear this called Hall's marriage theorem, that's why. Okay, so task 1, which will be like half of today, is just convincing you that Hall's theorem is actually true. So let's prove Hall's theorem. So I'm going to take my subscript I chose here was T for the total number of sets in my family. And I want to look at this Hall's condition, which says any union of k sets has size greater than or equal to k. And I want to say there exists an SDR if and only if Hall's condition is satisfied. So if and only ifs, we usually, have two steps to our proof, right? I prove one direction of implication and then I prove the other. Hall's theorem is one of the obvious necessary conditions are sufficient or the obvious sufficient conditions are necessary type theorems, where one of the directions is almost obvious and all of the work goes into saying the other direction of implication works too. So let's think about what the sort of easy direction of Hall's theorem is. And in the way that I've drawn it, it's the forward arrow. So if I have an SDR, like this, so I can pick out these different elements to represent each set, then if I take the union of, I'm going to write annoying things for this whole proof, like Si sub j, to say I'm picking out j ranges from 1 to k, so I'm picking out a total of k sets. Their indices don't necessarily have to be sequential, but their indices are like I1, I2 up through ik. If I look at this union, maybe I'll just skip to looking at the size of this union. I certainly could write like a set containment thing and then infer an inequality. But I can probably just see that, okay, if I have a subset of this stuff, and I can count how many things are in that subset, then the size of that subset is a lower bound on the size of the whole set. And how am I going to make a subset where I actually know how to count the elements? Well, I'm going to take distinct representatives one from each set. Because these are legitimately distinct, I know that I have a real set here. I don't have a multiset. So I was able to write down k distinct elements that are in this union. So I definitely have Hall's condition on my intersections. Okay, so the work of this proof is going to be showing the other direction if Hall's condition is satisfied, then we get an SDR. Okay. Previous section that I taught was sponsored by Red Bull. This is not sponsored by Red Bull. I already had 3 Red Bulls today. This is just sponsored by the department coffee maker. Okay. So, how are we going to do the more difficult part? There's multiple ways you can prove Hall's theorem. I want to tell a proof that's slightly different from maybe the standard proof, which is going to keep us just in this language of set theory, and it's going to actually do a little bit more than just showing that if Hall's condition is satisfied, then you get an SDR. It's going to do something like estimate how many SDRs you get in terms of how big your different sets are. So to do that, I'm going to sort of define some functions. The first function I define is going to be a function which takes an input of t numbers which I've ordered in a non-decreasing fashion. capital F sub t to tell me how many numbers to plug in of this non-decreasing list of numbers is going to be a product from I equals 0, sorry, t minus 1. I always pick, I mean, I've done pi day several times now, and I always feel like for the last thing I do, I pick something that has really annoying subscripts and indices, and there's going to be a lot of off by 1 errors that I write on the board here. If you see one and you think I did something wrong, just tell me. I probably did do something wrong. We're also going to have subscripts like mu sub I and nu sub I because we ran out of sensible English letters to use, so just like buckle in, everybody. We're going to get through it together. Okay, so my indices will go from 0 to t minus 1, so it's a product with t terms in it, and how do I get each term? I'm going to let this be the maximum of m sub I minus I and 1. So the first term in my product is m sub 0, if m sub 0 is at least 1. If m sub 0 is smaller than 1, then I just write a 1 there. My second term, I look at m sub 1 minus 1. If that's bigger than 1, I write that down. Otherwise, I just write 1, and I keep going along the line. So I like subtract a little bit more each time I hop to the next letter in my list. Okay, and what we're going to show is that basically I can use this type of function to count the number of SDRs in a family of sets that satisfies Hall's condition. The thing to really note by this definition, it looks a little bit confusing, but what do we know about this product? It's a product of positive, strictly positive numbers. It's actually, if the m sub i's are integers, it's going to be a positive integer because every one of these maxes would either be an integer minus an integer or just 1. And so it makes sense for this to be like a number of SDRs that I could find. It's not going to be -2 or pi or some weird number. Okay, so having things in non-decreasing order, if I have a list of numbers, I always can put them in non-decreasing order, but it might not be obvious if I have a list of numbers, they start in that order. So we just define lowercase ft in a similar way. If I just have a list of t numbers and I don't know about their ordering, what lowercase ft does is it says, put them in the right order, and then apply uppercase ft. So I find a non-decreasing order of the numbers that I plugged into lowercase f, and then I do this product. Okay. So let's observe one thing about these functions. Basically, what I'm going to try to do is apply induction in a second. So I would sort of like to know something about how these guys work if I change the numbers that I'm inputting. I don't need a very strong or difficult property. I'm just going to observe that lowercase ft is non-decreasing in each component, which is to say, for any component I that I fix, if I look at plugging in a list A naught through AT minus 1, and I think about what happens if I leave most of the list fixed and just increase this AI, I should get an equal or larger number when I do that. In particular, it suffices to show that, because I'm always going to be plugging integers in this, it suffices to show that if I plug in AI plus 1, I get the correct inequality here, AT minus 1. Okay, do we believe that inequality? I mean, it's a little bit strange because these aren't necessarily ordered correctly. And so you might be worried about, capital FT here and capital FT here. What happens to my non-decreasing ordering of a list of numbers if I add one to another number? But it's not really too bad to see that it doesn't mess things up. If I start with a non-decreasing ordering m0 less than or equal to m1 less than or equal to up to mt minus 1 of a naught through ai through at minus 1. What I want to do is kind of identify a place where I can say my ai plus 1 is going to slot in when I increase it that doesn't actually change the way that I'm ordering these letters. So let k be an index such that mk is equal to the ai which I want to increase, and either mk plus 1 is strictly bigger than mk. So if I have a bunch of repeated numbers in this list, then when I order them in non-decreasing order, maybe it looks like 1, 1, 1, 1, 1, 1, 1, and then I jump up to 2, 2, 2, 2, 2, and then maybe I jump up to like 4, 4. But I basically want to say AI is getting associated with the last thing in the list, which has the size of AI, which could look like it's some mk in this ordering, and then mk plus 1 is strictly bigger. Or if AI is one of the biggest numbers in my whole set of numbers, k could just be the last number in the list. Either way, notice what happens when I add 1 to mk. Mk plus 1 is less than or equal to mk plus 1 if I'm plugging integers in here. If I have two integers and one is strictly bigger than the other, then their difference is actually at least 1. So by just choosing carefully which of the terms in my non-decreasing list I want to associate to this AI, I can convince myself that when I increase this AI by 1, this is really ft of my original non-decreasing ordering, just with this mk incremented by 1. And now, okay, this is the product of max of each thing here. I take the thing and subtract I and see is that bigger than 1 or not. Most of the terms in this product are exactly the same as the terms in the original product that I would be looking at to figure out what ft of just a naught through at minus 1 are. The kth term, instead of multiplying by the max of mk minus k and 1, I'm multiplying by the max of mk plus 1 minus k and 1. So if mk plus 1 minus k is still less than or equal to 1, my kth term doesn't change. If it's bigger than 1, I'm multiplying here by a strictly bigger number than I was multiplying for just a naught through at minus 1. So indeed, non-decreasing, and it's going to be nice for us when we apply induction to just be able to look at one of these things and say, yeah, I can estimate this by taking all of the numbers that I plug into my ft function and plugging in smaller numbers if I want. Okay, so not the most fun thing to check, but hopefully not too strenuous. Any questions about this? Okay, cool. So that's kind of the setup that I need. I'm actually going to erase this now, I guess. It's an awkward amount of board work. So we know what we're trying to prove. We have these capital and little f functions. We now know a property of these functions. And so we're actually going to jump in to do an induction. Which shows that you can basically use these functions to count SDRs or estimate SDRs. Okay, so we have these functions. Little ft is non-decreasing in each component. And now we show if S satisfies Hall's condition, then the number of SDRs of S is going to be greater than or equal to f sub little t of the sizes of my sets plugged in there. In particular, if I satisfy Hall's condition, then the lower bound I get here is a number which is greater than or equal to 1. And so this says an SDR always exists, but if you want to, apply it for a specific family of sets, you can plug in their sizes and compute this thing. And if it's much, much bigger than 1, then you can say, okay, I am now guaranteed I can find at least like 1,000 SDRs in this set, if for some reason I want to pick and choose between them. Okay, so by induction on T, if T equals 1, well, I don't need to look at my notes here. How many systems of distinct representatives do I have of a family with one set in it? Yeah, there's definitely at least one, unless this is an empty set, in which case it's silly. So I'll say satisfying Hall's condition, so I know that the union of my one set has at least one element in it. Yeah, exactly. I can, for every single element, that single element is a distinct representative of my one set. There's like no conflicts that I could possibly have with another set. And this is what I get if I plug in just one number to f of 1, right? That's the non-decreasing order of my sizes. So I take the product with one term, and I take the max of this minus 0 and 1. So I definitely just get the size of my set. OK, so inductive base case works out quickly. That's nice. For the inductive step, fix t at least 2, and suppose this works for all smaller families of sets. This is another one where it is important to have the strong inductive hypothesis, because we're basically going to try to take a family of T sets and kind of partition it into two halves where I can apply the inductive hypothesis on both halves and somehow get like a product of two of these f functions, which I then infer is actually another f function in disguise or bounded by. But I'm not going to necessarily be able to guarantee exactly how this partition looks. Like, it doesn't necessarily have to have one element in one part and the rest in the other. Okay, so I'm going to have two cases. Relabeling if needed. My S sets are going to be indexed 0 to t minus 1, so they agree with my indexing on the f functions, and I'm just going to shuffle them around if I need so that they actually go in non-decreasing order of size. So we are going to have two cases here. One case is fun, the other case I'm like really dreading the notation. We're going to get through it, like I said, we're going to get through it together. So case 1. For any k smaller than t, so any positive integer that I take, which is not the whole size of my family, any union of k sets has size actually strictly bigger than k. So this certainly could happen if Hall's condition is satisfied. It could be that it's never tight. And if Hall's condition is never tight, so you look at the union of k things, you need that to have size at least k, but you always get even more than you need. You always get at least k plus 1. Maybe I'll even write this as bigger than or equal to k plus 1. Then we can pretty easily split apart. And the way that I'm going to do that is fix some element of my first set in the list. And I'm going to say, okay, that's just the representative for the first set. I don't always, in general, have the freedom to do this. it might be that it's, really important if I'm going to find an SDR that I pick one element over another from a certain set. But if I have this sort of non-tightness of Hall's condition, I'm claiming that I can just specify, okay, this X is going to be the representative for, maybe I'll even call it X0 to match the notation we were having before. This is going to be representative for X0. And now we consider S1 minus X, S2 minus X through ST minus 1 minus X. Okay, this is now a smaller family in terms of the number of sets that I see. I have T minus 1 sets in here, and for any k of them, the union size I'm going to get, okay, before I took X out from everything, I always got a union size of at least k plus 1. So now I've removed one element from each set, but I removed the same element from each set. So the only difference between unions in this new family and unions in my old family is if X was in a union. In the old family, it's not in a union here. So unions of these sets can drop by at most 1 in size. So I get at least k plus 1 minus 1 is k. So Hall's condition still applies. And by induction, there are at least, little f of t minus 1, but really it's just big F of t minus 1. They're the same. M1 minus 1 through mt minus 1 minus 1. Right, I plug in the sizes of my new sets. Every new set has, they've either stayed the same or decreased. So I guess it is possible that I had a change in the ordering here, depending on which sets contained X and which sets didn't. But as we talked about, this is a non-decreasing function if I increase things. So I can just sort of assume for a bound that every single set size decreased. And the reason why this is nice is that if I want to actually think about how many ways are there to get an SDR of my original set S, well, I have, by the product principle here, size of S naught ways that I could choose that X naught. And for every choice of X naught, now I have this F t minus 1 of M1 minus 1, M t minus 1 minus 1. And then if you think about what this product is, it's actually just exactly Ft of this guy with the minus 1s taken away. Right here in this product, I subtract 0 from this guy. I subtract 1 from the next guy in the list. If I shift M1 over to now be like the second term in this bigger product, I'm still going to be subtracting 1 from here and 2 from the next guy. So that's how my Ft is going to work. Okay, so that's not too bad. The annoying thing is case 2. where I can find some S. The news are the indices for my tight sets. So I get some set of K of these, S nu naught through S nu K minus 1, where actually the union of these has size exactly K. Okay, if that happens, say the rest of my sets are now S mu naught, S mu 1 through S mu T minus K minus 1. And I'm still going to have these in non-decreasing order of size. But these don't necessarily have to be, you know, the first K sets. They could be kind of circled from anywhere in my list. And these are the ones that I get when I just basically drop these and then say, okay, now I have a new smallest, second smallest, and so on. So what I want to now do is think about this family applying induction. And I'm going to apply induction to something similar than this family. I'm actually not going to exactly use this family. What I'm going to observe is if I have a subset where Hull's condition is tight, then any SDR that I picked would have to make an SDR of this guy, right, of the smaller guy. There's only K total elements in this whole union. And I need K different representatives for these K sets. So I need to use every single element in this union just to represent these K sets. So I definitely don't want to pick a system of distinct representatives for the rest of the things that overlap with anything in this union. So I'm actually going to define S primes. S prime of mu I is going to be this S of mu I set. Take away the union of all these S nus. So I take everything that was in this sort of subset where I know really specifically how the SDR has to look on that subset, and I take it out from all my other sets. Okay. I'm going to say observe these S prime of mu i's do still satisfy Hull's condition. How would you check that? I don't really want to write it down. But if you think about taking the union of some of these S prime of mu i's, you could kind of figure out that union by saying, go back to the S's and take the union of the corresponding S's plus all of the S nus. And you can understand what that union size is by the fact that Hull's condition holds on the whole original set. And then you know exactly what the union of these S nus has in terms of size. So you can conclude that you actually get the right number of elements in the union of the S mu i's as well. But again, don't really want to write that down. Corey asked me to be like slightly leisurely here, but there's like limits to how much detail we want to see at this time in the morning when none of us have gone to bed. In fact, I might kind of just assert my rights as the second to last lecturer and say that there's a few details that I'm not going to write down for you. Okay, so what's the important thing that we sort of get as an upshot there? We can conclude two things. The number of SDRs of my whole original set S that I've now broken up as these S news and these S mu primes. Well, again, this is going to sort of be a product of SDRs that I find among the S news and then SDRs that I find among the S mu primes, because I know that any SDR of the whole thing has to have exactly this form, that it looks like an SDR on this subset where Hall's condition was tight, using exactly these K elements, and then an SDR on the rest of it where none of the K elements that I need for the S mu sets are reused. So it's just the number of SDRs in my S new set times the number of SDRs in my S mu prime set. Okay, and now by induction, my first case sort of dealt with the case where I couldn't find a set of size strictly smaller than T where this worked. This thing has fewer than T sets. This thing has fewer than T sets. Hall's condition holds on both of these. So by my inductive hypothesis, this is greater than or equal to, okay, this little fk function I get where I plug in the sizes of all of those new sets times this, okay, I have T minus K sets in this second thing that I'm applying induction to. Their sizes are all either what they originally were down to like worst case scenario, every single one of them included every single element in the union of the S news. Again, sort of by this non-decreasing property, I can assume if I'm just going for a lower bound, the worst case scenario happened. And my index here will be T minus K minus 1. Okay, so I get some sort of inequality like that. And then I've written down another page of algebra, but it's really not satisfying, so I'm going to do this. What you just do is you play around with these things, and you sort of can figure out, okay, this part actually basically looks like the first half, or at least is bigger than or equal to the first kind of half of the product that I'd like to conclude this whole thing is bounded by. And then you fuss around with this part and you do some estimation of like what these indices can be relative to your original ordering, and you conclude that actually, if you think about what numbers you're multiplying here, it's the same as the sort of second half of what you multiply in the big product that we want to make a conclusion about. Do you believe me that you can do some algebra like that and it will work out? Okay, good, QED. Okay, so why are we talking about Hall's theorem out of all of the possible theorems I could talk about out of set theory? Hall's theorem, in fact, as I alluded to, is often thought of as more of like a graph theory result than a set theory result. But when we were thinking about interesting things in set theory, a thing that came to mind was this really striking fact that if you think about this as a set theory result, this makes cool connections between the realm of discrete set theory and lots of other sort of flavors of discrete math. So here's a list of 7 theorems, which are all, I mean, they're all named theorems, right? So these are all kind of big deal results. And as you can see, they span several areas. So the Koenig-Egervary theorem and the Birkhoff-von Neumann theorem on doubly stochastic matrices, those are both sort of matrix theory results. Koenig's theorem and Menger's theorem are both directly graph theory results. We did Menger's theorem last week in my introductory graph theory class that I'm teaching. Dilworth's theorem is about what we call partially ordered sets. Min-flow max-cut is something about digraphs. So we have a lot of different sort of named theorems here that are important in different areas of discrete math. And it turns out that all 7 of them are actually completely equivalent. Okay, I know in theory it's supposed to be that if you have any mathematically true statement, you can somehow logically convert it to any other mathematically true statement. But what do I mean when I say these are equivalent? I mean that it's relatively simple if I assume that one of the theorems is true to prove that another theorem is true. And I can sort of, for any pair of them, do either implication. If I assume the statement of one, I get the other. If I assume the statement of the second, I get the first. So for the last, what does Corey want me to do? Half an hour, 40 minutes-ish. What I'd like to do is indicate what some of these other results are and at least sketch some sort of proofs that we get these equivalences, starting with the Koenig-Egervary theorem. So we're going to show that Hall's theorem implies the Koenig-Egervary theorem, and I should start by telling you what the Koenig-Egervary theorem is. So this is something about 0, 1 valued matrices and how the sort of distribution of ones in them looks. So the term rank of a 0, 1 matrix is just the biggest number of ones that I can circle, so that anytime I circle 2 ones, they're not in the same column and they're not in the same row. And the cover number of my matrix is the smallest number of row column deletions I need to make to get a possibly square, possibly rectangular matrix that only has zeros in it. Okay, and we want to show that if we have Hall's theorem, then I can convert that into showing that the Koenig-Egervary theorem is true. Okay. Hall implies Koenig-Egervary. Well, just like in the proof of Hall's theorem, this is kind of a statement that says it looks a little bit different from what we said in Hall's theorem. Remember when we were proving Hall's theorem, we said one of the sort of implications is fairly clear. In all of these theorems, there's going to be sort of one direction of inequality, which is not that hard to check. In this case, let's say mu columns and rows together contain all ones in my matrix. In any set of ones with no 2 in a row or column together, each of my mu rows / columns that together contain all the ones I see anywhere contains at most 1, 1. So my term rank is certainly not bigger than the number of columns that I select here. So the more difficult thing is to show that the inequality goes the other way, that if I have a min cover of these columns, then I actually can find a set of ones to circle in my matrix where I get equality here. Okay. To show I can find a big enough set of ones, let's look at my matrix. I'm going to say something which hopefully you'll believe. If you play around with it for a second, you'll see that it's true, but it's a little bit annoying to write down, so I'm not going to. I can take my matrix and permute its rows and columns, and it's not going to change anything about how many columns I need to delete all my ones, and it's not going to change anything about my term rank. So I'm just going to assume that I've permuted my rows and columns if necessary, so that, say in a min cover, I delete R rows and S columns. I'm going to be able to assume that actually the rows that I need to delete, I've just shuffled up to the top, and the columns that I delete, I've just shuffled over here to the right. And so, okay, rows I delete, I could see ones anywhere along here. Columns I delete, I could see ones anywhere along here. I never delete anything that touches that square or rectangle in the bottom of this matrix. So there's only zeros that live here. And again, we're at the sort of sketchy part of the night, right? So let me draw some sort of picture to indicate without writing a lot of words why we can apply Hall's theorem in this situation. So for each row between 1 and R, I'm going to make a set. Si, which tells me what columns between 1 and n minus s intersect row I in a 1. So here's my row I. And I'm just going to say, where do the ones in this sort of upper left block appear? Okay, now the SIs need to actually satisfy Hall's condition. Why? If they didn't, I could find some set of k rows. Maybe it actually just looks like this. Maybe there's, say, 4 rows, and the union of these indices where they see ones in those columns is, say, 3. Well, what could I do? I'm assuming that these R rows and S columns I chose make kind of a minimal cover of these ones by rows and columns. But here, what are these 4 rows that I selected doing for me? They could cover many ones over here on the right, but all of the stuff on the right is also covered by these S columns. If these 4 rows are really only covering ones that appear in 3 columns here, I could delete those 4 rows from my cover and add 3 columns to my cover and make a strictly smaller cover. So for that reason, that doesn't happen because I have some minimal object that I'm looking at here. So I actually do have to have Hall's theorem satisfied by these sets that I cook up, which means that I have a system of distinct representatives saying, okay, for each of these rows, 1 through R, I can find a column index here where it's got a 1, and I find a different column index for each thing. So that's going to correspond to R ones up in this top block, where the ones, there's 1 from each row, they don't ever share a row, and I've set it up so that they don't ever share a column either. So that's half of the set of ones that I want to find to show what my term rank is. And I would just repeat exactly the same argument with kind of rows and columns flipped to say that I can find S ones down here in the bottom right that also are arranged like this. Okay, QED. And the rest of this lecture is kind of going to go similarly. We're going to see a famous theorem. I'm going to wave my hands for 5 to 10 minutes by drawing sort of a picture and indicating how I can convert one situation to another situation. So next up, Koenig's theorem. Oh, this is good. We don't actually have to wave hands here that much. So Koenig's theorem is about bipartite graphs. And that's another one of these minimax theorems. So there's 2 related objects you could look for in a bipartite graph. You could look for a matching, which is a set of edges where no 2 edges in your matching share an endpoint. You could look for a cover, which is a set of vertices, such that every edge in your graph has at least 1 endpoint in the cover. And Koenig's theorem says if you have specifically a bipartite graph, so half the vertices over here, half the vertices over here, edges can go between blobs, but they don't live inside blobs, then the size of a max matching and the size of a min cover are equal. And we want to show that the Koenig-Egerberry theorem implies Koenig's theorem. Okay, I did 3 hours on spectral graph theory. Maybe some of you weren't here, but if you were here, you'll remember that we have a nice way to store the information about a graph's vertices and edges in a matrix. So to apply the Koenig-Egerberry theorem to find matching and cover in this, what I'm going to do is convert to the adjacency matrix, which, if you weren't here and don't know, the adjacency matrix of a graph is a 0, 1 valued matrix where I put a 1 in the ijth entry if the ith vertex and the jth vertex of my graph make an edge. So I have some 0s and 1s here. So I have a 0, 1 valued matrix, so I can definitely apply the Koenig-Egerberry theorem to this to say its term rank is equal to the smallest row column cover of all the ones. And all I need to do is conclude that those 2 objects I'm trying to find in this matrix, a set of 1s where no 2 1s are in the same row and column, that's as large as possible, and a set of rows and columns that cover all the 1s and is as small as possible, actually correspond to a max matching and a min cover in this bipartite graph. Okay, so we can apply the Koenig-Egerberry theorem. So just need to observe that max matching corresponds to 1s in different rows, columns. And a min cover to one of these row column covers. Okay, that seems true, right? I mean, it seems true at this point in the night, at least, without writing any more down. If I have a matching, I've got that looks like, okay, edges correspond to ones in my graph, and if two edges don't share either endpoint, then they're not in the same row and they're not in the same column. So a matching is going to correspond to some set of ones that aren't in rows and columns together. And a cover is a set of vertices. Vertices correspond to rows and columns. And if I have a cover of my graph, it should be a set of vertices, so a set of rows and or columns, where every single edge is in one of the rows or columns that I choose, so is incident to one of the vertices corresponding to a row column. Okay, again, we're going fast, we're skipping details. That's what I'll say about that, but this is basically how the implication goes. Okay, last theorem that I'm going to state and show an implication for today is Dilworth's theorem about a totally different seeming type of object. So Dilworth's theorem is a theorem about posets. Poset stands for partially ordered set. So what a poset looks like is it's got some base set of elements, and it's got some sort of inequality relation. But it's maybe only partially ordered. So it's not necessarily like the integers or the real numbers, where any two elements you can say x is less than or equal to y, or y is less than or equal to x. We'll have some pairs of elements that have this inequality relating them, and the inequality works the way you think it should. But there could also be pairs of elements that are not comparable. Dilworth's theorem talks about two really natural things to do in a poset. One is to say, okay, in a poset P, how could I sort of sketch these relations? Maybe I start with, some element down here. Find something that's bigger than x1, find something that's bigger than x2. I can kind of draw a series of distinct comparable elements like this, and we would call this a chain. And then it's interesting to think about how few chains could you decompose a poset into. You could definitely decompose it into some number of chains because every element by itself is a trivial chain. But hopefully, you could, even if some elements are not comparable, you could compose it into some sort of long chains like this. So you'd have a picture that maybe sort of looks like this. Maybe I have a couple sort of short ones at the end. How many sort of disjoint chains do I need before I can have every element of my poset in exactly one chain? So this is a chain decomposition. On the other hand, what's an anti-chain? Okay, so a chain is a set of elements which are pairwise comparable, and you can sort of think about them as ascending in this fashion. An anti-chain is a set of pairwise incomparable elements. One way that you could potentially sort of visualize anti-chains occurring is if I've got sort of a bunch of chains, and maybe I think, okay, if I've got some stuff in a chain here and some stuff in a chain here, maybe those chains are like totally incomparable. You can just sort of circle one thing from a chain here and one thing from a chain there. In this kind of picture, it would just look like a bunch of dots with no edges between them. Okay, and And so again, we have this sort of minimax statement. The size of a biggest anti-chain that I can find is equal to the smallest number of chains that I need to actually decompose my whole poset. Okay, so given a poset P, I'm going to define a bipartite graph to which I can apply Koenig's theorem. And I'm going to want to define this bipartite graph in a clever way so that matchings will correspond, as it turns out, to chains, and covers will correspond to anti-chains. It's going to have two sides, A and B. And each side is basically a copy of all the elements in my poset. So I, for every element x in my poset, have an ax on the left and a bx on the right. And ax by is an edge if and only if x is strictly smaller than y. So if I have here ax, ay, bx, by, if x is strictly smaller than y, I add that edge in. Inequality does, in a poset, like I said, work the way you think it should. So if x is strictly smaller than y is strictly bigger than x. So I wouldn't have this ay to bx edge. And I also don't have edges when I have equality. I need strict inequality to make an edge. So for these four, there's exactly one edge in that picture. Okay. A matching in G corresponds to a chain. And the way that you can see that is okay, let's say I just start with some edge and some matching that I've chosen, axj, bxj minus 1. xj and j plus 1, sorry, do live in a chain together, right? This edge says that they're related. xj plus 1 is strictly bigger than xj. And so I'm just going to try to find more relations that I could use to build a longer chain containing this pair by finding more matching edges that kind of overlap in indices. And I'm going to do that until I can't anymore. So then maybe I can find a sub xj plus 1, and maybe it matches to some b sub xj plus 2. Eventually, I'm going to end that process. So find a biggest index k so that I can select a matching edge that kind of continues my chain building up like that. And I could also do it backwards. So I go backwards from J to sort of the smallest vertex that I can find that participates in a matching with this sort of arrangement. Okay, and now x1, x2, x3, up through xk is a chain. And in particular, I can identify that my chain starts at x1 and it ends at xk because I know that bx1 should not be matched over there. If bx1 is matched to something in M, then I can find like a strictly smaller element to augment my chain. And by the way, if axk were matched to something over there, then I could find a strictly bigger element to augment my chain. So every chain that I find by sort of finding a special submatching of this form is going to obviously start and end with like an unmatched vertex over here or over there if you prefer. Okay, so what that means is that the number of chains in my decomposition, every chain corresponds to, let's just focus over on the right, say, it corresponds to one element, the sort of bx1 that is showing the minimal element in the chain. It corresponds to one unmatched element over here on the right. So the number if I take a max matching, the number of chains in this decomposition that corresponds to my max matching is number of unmatched elements in B which is just the size of my poset, because that's how many elements are over in B, minus the size of my matching. Okay, so that's how I translate between chains and matchings. And you can also, maybe let's erase this, because now we know pretty well what a chain is. Go between vertex covers and antichains. So if I have a vertex cover of G, maybe I can even just say it's a min vertex cover. I'm going to make what I claim is an antichain in my poset. This is going to be all the x's in my poset such that AX is not in F and BX is not in F. So to say that that's an antichain, all we would have to say is if X, Y are in A and they're different, they're not related, then, well, okay, but this is immediate. This is, this F is a cover of all my edges. So AXBY can't be an edge because neither of its endpoints is in F by the definition of this A hat. AYBX, similarly, is not an edge. And so that means A is not strictly smaller than, or X is not strictly smaller than Y. Y is not strictly smaller than X. They're distinct, so they're not equal. So they actually are incomparable. Okay, so this is an antichain. And I can figure out basically how big it is. Let's actually apply Koenig's theorem. It says that the size of this min vertex cover is the same as the size of that max matching. So if I take size of my poset minus F, that's the same as the size of my poset minus M. And then the size of A should be bounded by this, because okay, I say that the size of A hat is bigger than or equal to that, because, okay, how many things are in my cover? Well, I could have AX and BX in my cover. But sort of, I think the worst case scenario here is my cover is just like a bunch of stuff from one side and not the other, in which case you can see that this would be exactly the size. Again, we're not going to go through details, but hopefully that's fairly intuitive without me writing down some inequalities. But that should be the case. So I get one inequality there on how big an anti-chain can be. It's going to be, the biggest anti-chain is going to be bigger than or equal to the number of chains in a smallest chain decomposition. And this is another case where we've actually proved the hard version of the inequality, that flipping the inequality. If you think about how anti-chains and chain decomposition should work. I can't take two elements from a single chain to be in my anti-chain. So I can take at most one element from each chain in my chain decomposition. So the other inequality is better. Okay. Now, briefly, the last thing, another QED. I think we have 4, right? We have Hall's theorem and 3 implications. I stated 7 theorems here, but obviously we do not have time to talk about what all 7 theorems say and prove all these implications. But let's sort of just notice what this proof technique for showing equivalences is doing. I've not actually been showing if and only if implications, but I don't need to as long as I am careful which implications I verify. So instead of saying, okay, for every pair of theorems on this list, I'm going to show 2 implications, what I could do to show that all 7 are equivalent is show just sort of a circle of implication. We start at Hall's theorem, which we proved, modulo some algebra that I didn't want to show you. I showed that Hall's theorem is true, and we sort of get on the circle and say, okay, Hall's theorem implies the Koenig-Egervary theorem, Koenig-Egervary implies Koenig, Koenig implies Dilworth. I could make a circle of all 7 if I wanted, but I would need to show that they're actually equivalent to show that from anywhere in the circle I can get anywhere else. So I actually do need to show an implication going back. So assuming Dilworth theorem, let's show that Hall's theorem is true. We already know Hall's theorem is true. We want to show that you can show it with Dilworth's theorem. So the last thing to do is to say Dilworth implies Hall. And again, if we're not pedantic about details, I think that this goes fairly quickly. So I consider a family of sets and I want to show that this thing has a system of distinct representatives if and only if all the sets satisfy Hall's condition. So what I'm going to do is what have we typically been doing? We translate to whatever the object is that the theorem we're assuming talks about, so we can apply the theorem we're assuming. So I'm going to make a poset out of this family. I'm going to say that these sets are all drawn from n elements, say x1 through xn. And my poset is going to contain all of my sets and all of the elements that make up the sets. So the actual set that my poset looks like is x1 through xn, s1 through st. And the way that I'm going to define my partial ordering is xi is strictly less than sj if and only if xi is in sj. And so now we want to say something about chains and anti-chains and use that to conclude that I can find an SDR if and only if Hall's condition is satisfied. Yeah?
Is it obvious that this order gives a closed set?
Well, I just need a set that has a, so as long as I get a partial order here, it's fine. So any two elements have to either be less than or one is less than or equal to the other, or they're not comparable. Okay, so I mean, implicitly, every element is equal to itself.
Yes, yeah. They're incomparable, yeah, individual elements.
Yeah, so all the xi's are incomparable, all of the sj's are incomparable.
Yeah, you never have the reverse.
Yeah, and it's clear that, yeah, I guess you'd be, you know, with inequalities, you want to make sure that you don't define something where like you get a circle of things, but this is never, it's not that hard to see that this is an inequality definition that works.
Yeah, in fact, it's like a biquadrant graph.
Yeah. And indeed, this was a good sort of discussion, because what does a chain decomposition of this poset look like? I can't have really exciting chains. Every S is only bigger or incomparable to every X. So I never have a chain that goes like X, S, X. And I never have a chain that has two X's next to each other because they're all incomparable. And I never have a chain that has two S's next to each other because they're all incomparable. So I can have chains with two elements that look like this. I could have chains with just one element. Or I could have chains with one element in the other flavor. Okay, so if I have k of these, then I have t minus k s's and n minus k x's left over. And so what's a system of distinct representatives? That corresponds to one of these chain decompositions where actually every S has a different X under it. So an SDR is a chain decomposition of size n. Right, I have k here, 0 here, so k is equal to t, and then elements left over maybe. So it suffices to show that I can find a chain decomposition of size n if and only if Hall's condition applies. And why is Dilworth's theorem useful here? The size of a chain decomposition that I can find is the same as the size of the biggest anti-chain that I can find. So it's actually easier to see that Hall's theorem works if and only if the biggest anti-chain you can find has size n. So let's just look at how we figure out sizes of anti-chains. So if Hall's condition holds, then I want to say that I can't find any anti-chain with more than n elements in it. Say an anti-chain A has k s's and l x's. If I look at the union of the S sets from my anti-chain, I get at least k different elements in there because Hall's condition is satisfied. So L, there's at least k x's that I can't put in. So I can choose at most n minus k. So I get at most whatever this k is plus n minus k. On the other hand, if Hall's condition isn't satisfied, then that actually just shows me how to construct an anti-chain with more than n elements in it. If I have k sets S, say just 1 through k, and their union has size smaller than k, then I take these SI sets and everything from the x's that's not in that union. So I have k things, and now this crosses off strictly fewer than k of my x's, so I can add at least n minus k plus 1 x's, and I get at least n plus 1 elements in my antichain. So I need a bigger chain decomposition of my post set, which means that I actually have some s's here that don't have x's under them in any chain decomposition. Okay, so again, everything a little bit sketchy at this time in the morning. I know it's a normal time for some people to be taking classes. I have not slept except for like a little nap in the last 24 hours. So hopefully if anything was slightly unclear, that's forgivable. I think these are really, really cool theorems, and is something that even if you've taken, graduate combinatorics class and you've seen most of these, it's not always commented on that all of these are actually just sort of different ways to phrase other things. Other theorems on this list, like I didn't know Menger's theorem was equivalent to Dilworth's theorem. Menger's theorem, in some sense, it would be great if instead of proving Menger's theorem to my students last week, I'd been like, I'm going to prove Hall's theorem, and then Menger's theorem is equivalent to Hall's theorem, because it's like easier to prove some of these than others directly. But they are all actually about the same. So maybe let's just wrap up by quickly. We have some conjectures here that are not related to these 7 theorems. But again, what was the sort of motivation for this? This was the obligatory discrete set theory sort of section. And we focused on one very nice result in discrete set theory that we saw has a lot of really, really beautiful connections. Here's a couple. One of them is like probably my personal favorite white whale conjecture. The first one is another very famous one. So union closed sets conjecture. If you have a family of subsets of the integers 1 through n, and they have a really nice property that anytime you take 2 of these subsets, their union is also in your family. Okay, let's suppose one sort of assumption to make this not trivial. Let's suppose that the empty set is not contained in this family. Then the union closed sets conjecture says that some element of your family should actually be contained in at least half of the things in there. This is like something that has its own Wikipedia page as a conjecture. There's quotes from like Gowers or somebody who's like, it seems like it should be obvious, but the inductive proof that you're thinking of doesn't work, or the averaging argument you're thinking of doesn't work. So it's one of the things I really, really love about these sort of discrete set theory questions is it can be very simple to phrase conjectures, and they can feel very intuitive, but they can be like shockingly hard to prove. The second I've listed as a problem. I could make a conjecture, but I would have to define some notation and like density limits and stuff, which I don't want to do. So I'm just going to say it's an open problem to figure out exactly the answer to this. Again, imagine you have a family of subsets of the first n integers, and you know a shocking amount about this family. Like you know some property that seems really strong. You know that every single set in this family has exactly 3 elements in it. And you know something really specific about how the sets intersect. You know that if for any 4 distinct elements in your base set, at least one of the possible triples is not in your set. How many elements can this family have? Again, it probably, if you've never thought about this problem before, you'd be like, oh, there's probably some sort of nice like averaging argument or something. This is, if you solve this problem, you would be incredibly famous instantly. This is in disguise an analog of the Turan number in what we call a hypergraph setting. And this is like big open conjecture. We think we know at least asymptotically what the answer should be, but people have been trying for like 50 years and used very sophisticated computing resources. And 80 years? Okay, yeah, I guess you're right. The hypergraph version is like the oldest extension of Turin problems. The first thing to do, and this is like the first problem to do. If you remember Mantel's theorem from earlier, this is like the analog of Mantel's theorem. Remember how Mantel's theorem we could prove in like 10 minutes? Yeah, so it gets harder when things get bigger. Okay, so that's what I'll say about set theory, and we have one more topic. So I'll turn it over to Corey and maybe a special guest.